Thank you for the invitation. And so I am going to talk on aspects of semi regularity map. This map comes into the importance of this map comes into the picture when you try to understand the variational Hodge conjecture. So, maybe I recall what is the variational Hodge conjecture. Very briefly. So, suppose you start with a smooth projective family. Okay, and now you take just take a point in here, and we look at the fiber. Now, there is since this is a smooth projective variety, there is a Hodge decomposition, and what we are interested in, we want to look at a closed subvariety. So, in my talk, so the conjecture holds for any, or it's stated for any subvariety, but I will write it in the setup that we will study in this talk. So, let me say restrict to the case that this is a local complete intersection. What this means is that for every point on Z0, you can find an open neighborhood such that Z0, so let us say this is of codimension P. So, what local complete intersection means, that we all know what is complete intersection, means that at every point in Z0 you can find an open neighborhood such that Z0 is defined by exactly P equations. And now, if I take say the cohomology class, so these are all part of the assumption, and we know that this will be a Hodge class. What it means to be a Hodge class, so there is a Hodge decomposition which I am not going to get into. Okay. And now the point is, as I deform this smooth projective variety along this family, means I am moving along this family, this cohomology class naturally moves as well due to Ehresmann's theorem. And what the conjecture says is that if this cohomology class moves in such a way that it remains a Hodge class, then that Hodge class will again come from an algebraic cycle. So, the conjecture states so I denote this thing is a such that for the deformation along B, gamma t is in that it is the cohomology class of algebraic of an algebraic cycle. Okay, where? So the original statement states for any subvariety. I am just restricting to this case because we are going to look at this local complete intersection. Now, of course, this is a conjecture, and if Hodge conjecture is true, which states that every Hodge class, so any element here we will call a Hodge class. So a Hodge class always comes from an algebraic cycle. That is the Hodge conjecture. So if the Hodge conjecture is true, then trivially the variational Hodge conjecture is true. But we cannot prove either of them. So let's see how far, what we can say. Now, what we can say is, let's restrict to, maybe I write a definition. So similarly in this setup, I have a smooth projective variety. So let's say setup. In here, I have a smooth projective variety, I have a point, and I take a local complete intersection. Now, I will say, we say that the pair satisfies and the effective Hodge property if, so let me write this statement in the first order infinitesimal deformation case. This can be done more generally. For every tangent T in here, and for every tangent vector here, I will get an infinitesimal, first order infinitesimal deformation of this object. For every, we have that gamma 0 deforms as a Hodge class gamma t x t if and only if z0 lifts, or yeah, z0 lifts as a local complete intersection So what is this saying is just that I have the deformation, normally it's written in this way, okay. Now I have local complete intersection in here. Now, of course, if you take the image in here, that is not going to be a local complete intersection, but what this statement is saying is that we will say that this pair has an effective Hodge property if and only if for the cohomology class will lift to a Hodge class. I will make this statement precise, what it means to be a Hodge class on an Artinian ring. And so this thing lifts to a Hodge class if and only if you can lift this object. This is what this statement is saying. Easy examples are if you take B, let's so this is the parameterizing space actually I want to take parameterizing space of smooth degree D surfaces in P3. Okay, I take a point in here and B and is a smooth projective curve of degree less than D minus 4. So you don't have to worry about it. Minus 4 comes from some canonical class. But this is an example, and it's not totally obvious, but this is not hard to prove either. Now, counter example. So this is for any t. Any t, it will, because of some, so it will have, so I can say that Z0, X0 has the effective Hodge property. So for any infinitesimal deformation of this pair, the cohomology class of Z0 will remain a cohomology class if and only if this curve lifts as a local complete intersection. Maybe I should take D greater than or equal to 4 to be safe. 5. Okay. Now, typical counterexamples comes from, so let's just look at in the surface case. So typical counterexample, so if I have a curve, this curve, because this is a divisor, and so it corresponds to a line bundle. So typical counterexamples will come when the linear system, the dimension of the linear system of this line bundle, the dimension jumps. So typical counterexample will be like if you have a family as before, and you take L triple sheaf on here, and now suppose you have, if there exists in B such that the dimension or H0 of, so by this one I just mean the restriction of this line bundle on the fiber over 0. This thing strictly greater than H0 LB. Similarly, this thing is equal to. Okay. And the reason this is very simple is that when you take an infinitesimal deformation of X0, you will get an exact sequence of this form. You will get an exact sequence of the form. And now if you take the global sections, you will get now this map in this situation is almost never surjective. And what this will tell us is that, so this parameterizes all the Cartier divisors. This parameterizes all the Cartier divisors in X0, And this map not being surjective means that there is a effective Cartier divisor which does not lift as a local complete intersection. So there are explicit examples, but I'm not going to go. It comes in a similar way. It is not hard to make this more explicit. Okay. So now let us look at this. But the point is that this property is captured by something called the Semi Regularity Map, and these examples Z0, these examples are actually examples of some things which are called semi regular varieties, and semi regular varieties satisfy this property. It is a very strong property, and it is not if and only if. So let me try to recall what is the semi regularity map. Let me first say what is in the easy case. This is the classical case known after Kodaira-Spencer, semi regularity map for devices. This one comes from if you just take the short exact sequence. So what is the setup? So my setup will always be like before. I have a family of smooth projective varieties, and I take a base point in B, and I look at the fiber over that point, and I look at here I am looking at a divisor in that variety. So say this is an effective. Actually, you can forget about Cartier because this is a smooth variety. So all divisors are Cartier. Now, here you will get a short exact sequence. This is the natural short exact sequence. Maybe I write down how you get. This is a very easy. This we all know. This is the ideal of Z0 in X0, and this short exact sequence we know, and then you just tensor it with. So apply this to this short exact sequence, and you will end up with this. This is the normal. Okay. Actually, this is of rank 1 because this is an effective. This is a divisor. Anyway, so now the semi-regularity map. Actually comes from the boundary of this short exact sequence. Okay, this is called the semi-regularity map. Let's denote this by pi. And we say that Z0 is semi-regular in X0 if the semi-regularity map is injective. Okay, so for the divisor case, now we know. Now the application of this, how this comes into the picture, maybe I will be able to say about this example, is what you start with, we always have a smooth projective family. That means that it is embedded inside some projective space, each of the fibers. So, what I am saying is, by the definition, okay, there are too many pi's, but let's see. Now, what you can do is I will give a black box for people who do not know. The tangent space to the Hodge locus. Associated to so what this is saying exactly what I in some way wrote here. These are in some sense T in T0b such that gamma 0 lifts as a Hodge class. So, this is kind of the meaning. So, gamma 0 is the cohomology. So, gamma 0 is the cohomology class of Z0, and this is the deformation as I move this. Okay. This can be made pretty precise, but there is a nice way of computing the tangent space that is using cup product. What I can do is that I can take H. Okay, so another thing that I have not said is that this is, so now we are working in codimension 1. So, we had a PP before, we were working in codimension P, now here we are in codimension 1. So, this is actually the 1, 1. Okay, and now we all know that the cup product will go to H2, okay, and now the cohomology class of Z0, which is lives in here. And the tangent space, which let us call Hodge locus. I use Roberto's notation. This is the kernel of which is simply so this is 0 in here. Okay. Now, this space parameterizes all the infinitesimal deformations of this smooth projective variety. So, we know that H1 all. So, here I am always in the algebraic situation. These are all algebraic. first infinitesimal of. Now, this space could be much larger than B. So, now we have to somehow relate the tangent space at a point on B to this space, and that is given by the Kodaira-Spencer map. So, there is something called the Kodaira-Spencer map, which is not hard. This is and that relates the two. Now, let us, since these are all projective, smooth projective varieties, and this is a flat family, so in particular this is a smooth family. So, they all lie in a particular Hilbert scheme. So, this object is actually contained, let us still call that base point O, in the Hilbert scheme of the correct Hilbert polynomial in P n. So, in case somebody does not know about Hilbert schemes, and you can also look at flag Hilbert schemes. This come from a functor. So, in this case I have to fix a Hilbert polynomial, and as soon as I fix for fixing a Hilbert polynomial I need an ambient space, which I take Pn in this case, and this goes from, I am always working, this can be done over any field, but for now I am working over C, where I take let us say S, and here I look at and here I just assume that this is flat. So, here it need not be smooth. Similarly, for flag you can have more than one Hilbert polynomial. You can have P, let us say the case of 2. So, these are just these are called the functors. These are the functors, and the point is that these functors are actually representable. So, they uniquely give you the Hilbert scheme or the flag Hilbert scheme, the universal object. Here you can take pairs. Similarly, these are all flat. Okay. So, now what I can look at is this. I am going to study this object because there are a lot of tools for this. So, what I do is, we know this is the theorem due to Grothendieck. Is that this is of the form H0 of Dn. Okay. Now, what I can do is that I can naturally go, I have a map from this object. In the case of divisors, going to, and this map is given by, you first take an element in here, say T prime, you send it to, first I take the Kodaira Spencer map and I gave here the description using the cup product. Okay. So, this in some sense, actually this is exactly all the, this consists of all the infinitesimal deformations of x0 along this family, such this one can have more, but in some sense this this consists of all the infinitesimal deformations of x0 inside Pn, such that the Hodge class gamma 0 lifts as a Hodge class. Now, what is our goal? Our goal is to see how close are we to the variational Hodge conjecture, or okay, not the variational Hodge conjecture in this case, but the effective Hodge property, because the variational Hodge conjecture is true in this case. We are in divisors, we have Lefschetz 1, 1. So, here, now here, I have a semi regularity map. Yes. Now, I just need to go from here to here, and that is not hard. So, I first restrict to, this is a natural map. This is a natural restriction map. Now, here I have a map, and this map is coming from a short exact sequence of the normal sheaves. I'm making a mistake. So, here you see, if you take the boundary map of this, the global sections of this is here, and the first cohomology is here, and this is really this map, and we can show this is commutative essentially by a result of block. So, this is, you need to work a little bit after Bloch's result, but that is the main idea. Now, what do I want to say? Maybe I work out that example. Do I want to work out that? Yeah. So, now let us look at surfaces in P3, very concrete case. So, x0 let us say is a smooth degree D surface in P3. Okay. Now, let us take a smooth curve in here. So, and there is another hint that I need to say is that since this is a complete intersection, n of x0, this thing is isomorphic. This is a standard result, I think, in complex algebraic geometry. Now, if you just use this, what does this restriction map becomes? This restriction map becomes of O, sorry, here should be x0, D, and then I am restricting this to O. Now, this very much looks like it is coming from a short exact sequence. So, of course, this is coming from a short exact sequence, and the kernel of this map is O minus Z0 of D okay, and this one is 0. This is not hard to check. This is exact. Now, here I am using this. This is a classical result of Castelnuovo. Yeah. It says that there is something called the regularity, not the same as semi-regularity, which says that if you have a smooth curve in P3, then after a certain degree, the cohomology of the ideal sheaf of that curve will vanish. So, it is called the Castelnuovo-Mumford regularity, and if this is smooth, the regularity. So, now here I have to say that this smooth curve is of degree. So, for this I just need D. So, if this is of degree D, degree less than equal to D, this thing will vanish. Okay. Now, here now is the next part of the story. So, this one is surjective now. Okay. Okay. Now, this one again we saw comes from another short exact sequence, and the previous element of the short exact sequence is here. It is the H1 of this object. Okay. Now, again here as well I will get 0, but now here if I apply, so this is some. So, if I apply Z duality, I will get in a similar situation like here, but instead of D I will get D minus 4, and this is because the canonical divisor is isomorphic. And here this for similarly for the same reason, for this one to vanish again by Castelnuovo, here I need D minus 4. So, this means that this is 0, this means this is injective. So, conclusion, is that Z0 is semi-regular and can we see directly? Let us see. Right, yes, we can. So, this one I said comes from this short exact sequence. So, let me just erase a bit here. So, yeah, this is the example. This is I am elaborating, I am just putting an example out there. Okay, so this one was the boundary map, and the thing that is before this is the global sections of this one. Okay. Now, here there is a result in deformation theory which says that if you take the fiber product as a vector space, just as a vector space, if you take the fiber product, this is actually the tangent space okay, I'll explain this. It's looks a bit ugly. So this object is the Flach-Hilbert scheme that I said, which consists of all the pairs of deformations, all the deformations of this pair. So the tangent space parameterizes all the infinitesimal deformations of this pair. In particular, it parameterizes the image of this map. The image consists of all first order infinitesimal deformations of x0 such that z0 lifts as an effective Cauchy divisor. So here I really need to mention effective Cauchy divisor, because here the infinitesimal deformation of x0 is highly non-reduced. It is nowhere close to smooth. So the image of this parameterizes all the infinitesimal deformations of this smooth projective variety such that z0 lifts as an effective Cauchy divisor. And now you just have to check that the image of this is actually the kernel of this. And for this, you just need the injectivity of this, the exactness of this, and the surjectivity of this. So check. Let's call this row 1, row 2, image of row 1, row 2, with, in other words, that the effective Hodge property is satisfied. Okay. Now, for this, you just need to do this diagram, and I want to. So I have 5 more minutes, right? Huh? Oh, I see. So it's complete 1 hour. Okay. 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 Good. So then I can say a bit more. Yeah, so there are infinitesimal. You can do infinitesimal by very similar. I had written the thing, but I decided not because it was too technical. But you can do very similarly. You can do for all infinitesimal deformation, very similar. The Bloch has written, in Bloch's article, the whole infinitesimal case is studied in details. I had thought of saying that, but I think it was a bit, could have been too technical. So let me say a general theorem. Well, maybe I try to write the actual definition of, in general, the semi-regularity map. So if I take Z0, so this I am trying to say semi-regularity map. This is not the original, this is not the definition, this is more of a property, but this is more check cohomology. The other one is a bit more algebraic. So I'm sticking to this one. Let's see. Local complete intersection of codimension P. And now we know that there is a the cohomology class of Z0 has a description in check cohomology using just first you can write a class Z0. Okay. Here I am going to use something. So what do I mean here? This is the local cohomology with support in Z0, which is just you take, just like in the normal case, you take a sheaf, you take the right, normally when you take the cohomology, you take the right derived functor. But here what you do is that you take Ri of global sections supported at Z. Normally you just take the global section, here you take the, and you apply F. And this will give you the cohomology. And this is the sheaf theoretic. So what you just need to do is that you just need to do this construction locally. So local construction is going to give you the sheaf theoretic. So this is a group, this is a sheaf. Just for notation, making the distinction. Okay, now what we also know is that if I have a locally free sheaf here, so this is the well-known result, is that if locally free, then H in this situation, okay, codimension P, HQ if is 0 for all Q not equal to P. Okay, and now you have the I think the Grothendieck spectral sequence, which says that, sorry, otherwise it's always 0. And the spectral sequence says that there is a decomposition of this object in terms of this object. So there is a which says that H Q Z naught of F. Here you can take any sheaf of abelian groups. So here for F sheaf of abelian groups. And here you can take Q minus I direct sum over I okay. And now if you combine with this result, so this tells you that if F is locally free, then HQ F in particular, we can apply this to this case, which will tell us that HP, I did not give you the construction. This construction is very standard. You can see in Bloch's article. I think the article is called semi regularity, and then I'm cohomology. This is a very easy description using check cohomology of this cycle. Now, so HP of Z0 omega p, this by the this result is just the global section of okay. So now I have this in here. Actually, this will be a global section in here. And now there is a natural map. This is and it's a result that the image of this is just the cohomology plus Z naught. And then the semi regularity map, let me see. So, okay, we need to do a bit more. So, I take the normal bundle of, so this is the and I want to write a map to HP Z naught of. So, as you can guess, this is in some sense inner product. So, what I am doing here is that let us just take a open affine subset. Open affine. Now, a section of this in this open affine is just something which goes from the ideal sheaf okay. And now I want to map this to. So, let us say that on this open subset, suppose Z0 is defined as the 0 locus. So, I said that this is local complete intersection. So, I can always take the open affine small enough such that on that open affine Z naught is a complete intersection. So, I take that this is the 0 locus of some P equations in X. Okay. Now, here what I am going to do is alpha I of Fij. So, I am here now, but I want to be on X0. So, I take the lifting. By lifting, I just mean that I have a natural map, surjective because this is affine, and here I have alpha I of Fij, and I lift it to alpha I Fij tilde. So, of course, this lift is not unique, but the difference of any two lifts lies in the ideal sheaf of Z0, and because of that, this object, anything that is a multiple of an ideal sheaf of Z naught will vanish here. So, what I am trying to say is that this element gives a well defined element in here. This So I forget about this. This gives a well-defined element in here which does not depend on the lift. Okay, now let's call this map, okay, and we are now very close. Okay. Now, the semi-regularity map is simply I apply the semi-regularity map, maybe I call this pipe ring. Going from to H1 of prime to HP now we saw there that this should be isomorphic to HP plus 1 and there is the natural map to HP plus 1 of omega p minus 1 and this is called the semi-regularity map. And if this is injective, then it is called it's called semi-regular. So it is important here that it depends on its embedding inside the surface, and I'm going to end with the theorem of Bloch, which says that if any semi-regular pair satisfies the effective Hodge property, in particular the variational Hodge conjecture. I stop.